Thank you. My name's Luke, and I'm going to be telling you all about a new open source project called Snabb Switch, which is all about building open source network elements to help build the internet. Before I start, I'd like to introduce myself. I'm from Australia, but I live in Switzerland these days, and I'm the one who started the Snabb Switch project originally. And my experience professionally is mostly working in network equipment vendors. I spent a long time building products like firewalls and VPNs and these kind of things as kind of appliances that are sold to network operators. And then I've also had a kind of a completely different set of technical experiences apart from work, working with some kind of unusual technologies. So I worked at the very first Erlang startup company in Sweden when Erlang was spinning out of Ericsson. And I did a lot of Common Lisp programming for a while. I co-created an IDE for Common Lisp called Slime that's fairly popular. And I did also some other kind of unusual hacking, like writing device drivers in some strange languages like Forth on the one laptop, a child laptop, and in Smalltalk with one of Alan Kay's research projects. So I've been doing a lot of hacking and a lot of different things over a long time, and I decided I needed an open source project that could combine together all of these things. On the one hand, the ideas that come from building network equipment and being responsible for deploying it and fixing it when it goes wrong and integrating it and making everything work. And on the other hand, getting exposed to a lot of interesting ideas from high-level programming languages and kind of modern ways of writing software that are a bit different than what's normal in the networking world. And that's how Snabb Switch got started. So what I want to cover today is, first of all, what's it all about? What's the point of the project? Who is it for? What is the context? What's it all about? And then to go in a fairly reasonable level of detail about the software architecture that we use, so that you understand in a high-level way what is Snabb Switch technically. Does it have any ideas that you can relate to, or might be useful as an inspiration? And then after we've kind of gone through the software architecture, then to look at a couple of actual real applications that we've built on Snabb Switch and show how they work in terms of the software architecture. So the context that Snabb Switch exists in is the network equipment industry. This is all of the stuff that the internet is built out of. So I'm talking about the kind of network devices that you find in an ISP or a university or a large company or a data center of a hosting provider and that kind of thing. So there's all of these different products that go into building up the internet. You have switches, you have routers, you have firewalls, you have GGSNs, you have SGSNs, you have RNCs, you have hundreds and hundreds and hundreds of different products. And people are running out and finding products that need to be built and building them and selling them. And it's a massive industry with a lot of kind of cool stuff going on. And it has been for a long time. Always kind of been kind of dynamic with a lot of interesting things happening, but something that is totally lacking in this whole area from my perspective is open source software running on normal x86 servers. So in other areas like databases, it's a completely normal thing if you want to deploy a database that you would go out and buy a server and fill it up with hard disks and then download some open source software and deploy that. This is the most natural thing in the world, but this is not something that's happening in the networking industry. Rather, people buy proprietary products and hardware, and I think the idea of solving high-end networking problems with x86 servers and open source software is an idea whose time has come, and that's kind of what Snabb Switch is addressing. So when we say an x86 server, just to be a little bit more concrete, this is what an x86 server looks like if you would want to do a lot of networking on it. So this is, I guess everybody has seen servers in racks that maybe have a lot of hard disks. You look at the front panel and you just see a bunch of hard disks running a database or something like that. So this is the networking equivalent of such a server. It's just got all of the PCI slots filled up with network cards. So in this particular server, it's got 2 CPUs and it's got 10 network cards, and each network card has 2 10 gigabit Ethernet ports. So that's 200 gigabits per second of Ethernet bandwidth on a server, which is quite a lot. So if you walk around a data center of an internet provider or any kind of a big network, and you just look at all of the network elements and count the number that need more than 200 gigabits per second of bandwidth on one in one box, it's not very many. So you can, in pure I/O terms, you can address a lot of problems with a server like this. And the kind of cool thing that is becoming more widely known just recently is that you can actually, on a server like this, you can actually drive all of those ports at full speed at the same time using ordinary software. So Intel have done a huge amount of work in improving this to the world, and now we kind of know that. We know that on a server like this, you can process all that traffic, which is a huge deal when you think about it, because with 200 gigabits a second of traffic, you're looking at a packet arriving on the server in a realistic workload, something like every 10 or 20 nanoseconds. And 10 or 20 nanoseconds is not a really long time to get something done. And the amount of bandwidth is growing as well. So the next generation with PCI Express version 4, you'll have a terabit of bandwidth in a server like this. You would have 10 100 gig ports. So the arrival of packets is just insane. And the way that you have to address this is with particularly designed software. So you have to write software in a different way. You have to basically say, on a server like this, you have 20 10 gigabit Ethernet ports. You need to have 20 CPU cores, and each CPU core will be running software that drives one of those ports. And any interaction between these processes has to be as absolutely minimal and streamlined as possible. You absolutely are not allowed to take locks that block all of the cores and this kind of thing. So it's a very interesting challenge. If you do manage to divide your application up like that, matching a port up to a core, then you have more like a few hundred nanoseconds to process each packet, and in a few hundred nanoseconds on a CPU, you can process maybe 1,000 or 2,000 instructions, and that is actually a reasonable budget. So this is the reality that we live in. Every time a packet comes in, you can spend 1,000 or 2,000 instructions on processing it, and you can do something interesting. And then as the exponential growth of bandwidth keeps going up, you will have exponential growth in CPU cores to keep your per packet processing budget kind of fixed. So this is the reality of network programming today on such servers. Okay, so that's the hardware and kind of like software in the abstract, but what about actual software? So if you go out and you buy a server like this, which is not that expensive, a server like that costs about $10,000. It has 200 gigabits per second of bandwidth, and they're getting cheaper all the time. So you go out and you buy a server like this, you've got your 200 gig, you hook them all up to your network, then what are you going to do? You need some software to run on the server. Now you can't just apt-get install all that much software that can do anything at all at really high bandwidth like this. So if you would just install Linux and just take a bunch of IP tables rules and just try to do a normal kind of run it as a firewall or a router or something like that, you will get not at all high performance. You probably have to push to even get something like 10% utilization of so much hardware. And this is a problem that's going to get worse and worse as the bandwidth goes up, because you're just not allowed to write software this way anymore as a large monolithic multi-threaded program that's taking a lot of locks all over the place. That worked very well with low core counts. It doesn't work very well anymore, and it's going to work very poorly in the future. So that's where Snabb Switch comes into the whole picture. We need some software that you can just apt-get install that will do something that you want to do in a network and you can deploy on kind of high-end networking hardware. And we are an open source community that is just building a bunch of these applications. So we've built a load generator, for example. Somebody in an ISP is building a virtual private LAN service. This is so that he can replace his Cisco routers with PCs that he can program, or x86 servers that he can program in a more flexible way. We built a big network functions virtualization system to connect VMs very efficiently to a network for a huge telco. And basically, we're an open source community that's just trying to solve the kind of problems that an ISP or another network operator would normally need to go out and buy some kind of high-end piece of equipment. So the idea is that you go out, you buy a server, you load it up with network cards, you download our software, you install it, and you're on your way. And you save the whole problem of finding a vendor who you're going to pay $1 million or something for a proprietary solution. And when I say we, I'm really talking about a grassroots open source community. So there's a lot of different models for open source these days, and there's a lot of kind of large consortia with a lot of vendors and platinum memberships and all of that kind of thing. That's not what we are. We're kind of like Linux was in the early days, you could say. It's a grassroots project that grows one person at a time as the technical person thinks that this looks like a project that they could solve a problem with, and everything is just kind of organic in that way. And within the community, we have a few different kind of sorts of roles for people. There are some people who are actually working in network operators. So their job is to go somewhere, build and maintain a network, and provide networking services to people. And these are the people that really give the whole project some kind of a meaning, because they're the ones who actually have a problem that needs to be solved and a use for the software. And then to support these people, we also have a whole bunch of independent professional open source developers like me. So I'm one person doing, working professionally building Snabb Switch applications, but there are a lot of others, both individuals and companies, who can support network operators. So the model there is that I'm a network operator, I want to deploy something, I'm not happy with any of the proprietary solutions, I want to have something open source that's going to fit exactly my requirements and I'm going to be able to customize. I can then decide how much of the project I want to do myself. Do I want to just create a high-level design and find somebody from the community who can build the whole thing and support it for me, or do I want to build a prototype and then hand it over to somebody, or do I want to do the whole thing myself and just call somebody if I get in trouble or whatever? So we have a lot of people who help each other in that sense. And then also, because it's an open source project, we also have a whole lot of just creative people on the internet. So anybody who thinks that the kind of technology we work with is interesting is always welcome to come and join in and make contributions. Okay, so that's the context. There's lots of problems to solve in networking. There's this exciting new hardware. There's no software yet, so we're building the software. And we're building the software, we're not just building any old software. So we're building the software in a very particular way. We're trying to make things very, very simple while still acknowledging the kind of fundamental difficulties of the problems that we're addressing. So the Snabb Switch software is unusual in that it's at the same time both very high level and also very low level. So when I say that it's high level, I mean that it's written in a programming language called Lua. Lua is a really, really simple programming language. If you're familiar with Python or JavaScript or Ruby or Perl or C or any of these other languages, then Lua is kind of similar, but just a lot simpler. And we use a just-in-time compiler called LuaJIT that is just a phenomenal piece of engineering that can take Lua code that's been written with some care and actually make it run at speeds competitive with C. It means we hardly ever have to use C code, even when we're counting cycles. And then on the low-level side, we also really into being self-sufficient. So we write our own device drivers, for example, and we write them in Lua. And the reason for this is that we just want to have everything in one place. We just want to have things simple. So a part of the character of the system is that if we need, for example, to drive an Intel 10 gigabit network interface, we'd much rather spend a bit of time writing some hundreds of lines of code to drive that, and then have the problem solved and have a complete understanding of everything, rather than take a vendor library and link it into our process that might be 10 or 100 times as much code and have its own release cycles and all that kind of thing that we need to fit in with. We also avoid a whole lot of really kind of complicated concepts like threads, locks, interrupts, and kernel modules. So if you think about doing networking on an x86 server, you're probably thinking about the Linux kernel, for example. And if you want to do programming on the Linux kernel, then you should read a 500-page book that tells you all of the things that can go wrong so that you can be very careful in the way that you write things and you don't make any mistakes and crash the server. We don't use any of those complicated concepts. So if you want to do really, really kind of high-performance networking with Snabb Switch, you just don't need to know any of those things. You can just learn Lua and get moving. Another kind of part of the character of our software is we're really, really, really concerned with trying to do more with less. So from the very, very beginning, we've wanted to make sure that we always have software that's kind of simple and comprehensible and that one person can fit in their head. And so we put some self-imposed constraints on this from the beginning. So we said that the software should not be more than 10,000 lines of code in total for all of the shared code base that we really expect everybody to be able to understand and troubleshoot. We also said that you should be able to compile Snabb Switch in 1 second, just to make life nice. You shouldn't be spending your whole time waiting on compilation. And to keep our dependencies under control, we said that if you include all of the dependencies, like the Lua virtual machine that's written in C, you should still be able to compile the whole thing in not more than a minute with one core. And finally, we decided that it's very easy for the size of applications to blow out, right? In the age of containers, you can kind of link a whole operating system into your application these days. We don't want to do that. So we said that when you compile Snabb Switch, you should get a single file of 1 megabyte that will run on any 64-bit Linux server, regardless of what kernel version it's using and regardless of what exact CPU model it has. It should be very, very standalone, easy to deploy. And with having kind of described the character of it, now we can get into the details of how the actual thing works. So most work on Snabb Switch designing applications is done on a whiteboard. It's our fundamental kind of fundamental software design tool. And this is a picture of how a simple application based on Snabb Switch would work if you design it with a whiteboard. So here we have an illustration of an application that has 2 network interface cards. This would normally be 10 gigabit cards. And then it has a filter application or app. And when a packet is received on NIC A, it has to pass through the filter before it's allowed to go out on NIC B. But when a packet is received on NIC B, it's allowed to go straight over to NIC A. So this is a picture of a network device that has 2 Ethernet interfaces and filters packets in one direction and not in the other direction. And I just want to use this to illustrate the basic concepts that we have in Snabb Switch in the core. There are really only 3 main concepts in the whole main abstraction. One is an app, which are the NIC and the filter that you see in this picture. So an app is the unit of functionality. It's some code that does something with packets. Another is a link, which is a way that packets go from one app to another. It's how you say when a packet comes from this, is processed in this way, it needs to go here as the next step. And the last concept we have is a packet, which is the unit of information that passes over a link. And I think you can think of this as a close analogy to the Unix model, where in Unix you have processes, which are like our apps, and you have pipes that are like our links, and you have packets, well, they have text. So what I'd like to do now, I keep insisting that Snabb Switch is a simple program, so what I would like to do is just show exactly how these things are represented to kind of put my money where my mouth is. So this is the definition of the packet structure that we have. So a packet is defined as a C struct, which is actually fine for Luajit. It can deal with C data structures exactly as easily as it deals with Lua data structures. And the packet has just 2 fields. It has a 10 kilobyte array where you can put an Ethernet packet, and it has a length field where you say how much of that you're actually using. And that's it. This is basically the same representation of a packet as you would find on a physical Ethernet cable. It's just the bits that make up the payload, and that's all. And there's not really a lot more to say about this. If you're writing Snabb Switch code, this is the data structure that you're operating on. There is a whole bunch of library code that you can use for finding headers and all of that kind of thing. But that's just libraries, and that's all optional. And I think this is a big difference than a lot of other systems, like the skbuff struct in Linux, for example, where you might have 100 different fields or more with a lot of locks and a lot of metadata and a lot of kind of complicated rules that if you make a change in this part of the packet, you also need to update all of these other fields and hold these locks and that kind of thing. So we don't have any of that. So if you want to manipulate a packet in Snabb Switch, that's what a packet is. You can just operate on it in memory in any way that you like. A link is not much more complicated. So a link is represented in memory as a circular buffer. It's got a little array where one process is writing packets and another function is coming along reading the packets off. And if the read pointer tries to overtake the write pointer, then the link is empty. And if the write pointer tries to overtake the read pointer, then it's full, and that's kind of it. You can read the Wikipedia page for a circular buffer to see the whole thing. And then we have the apps. So apps are the things that actually make things happen, right? So a packet is a completely passive data structure. It's just a representation of a packet that's being transmitted on a network. A link is a passive data structure. It's just a FIFO buffer giving packets from one app to another. And an app then is a Lua object that just implements a couple of callbacks that are driven by an event loop. So the way that our event loop works is what we call the breathing cycle. So at the beginning, we pull in packets to operate on, like pull in packets, and then we push out all of the packets back onto the network. And this is done with these 2 callbacks. So what the event loop does is it looks at all of your apps. It calls the pull method on every app. The pull method has the opportunity then to pull in packets from the outside world for processing and put them onto a link. After that's done, then you have some packets, maybe 100 packets that you're going to operate on. Then it just calls the push methods on all of the apps, and they can look at their link, see what packets they have to do, and decide what to do with them. They can drop the packet, they can transform it, they can pass it on to the next one, they can write it out onto a physical network, anything. And the way that this kind of executes in a normal application is when you do one of these breathe cycles under heavy load, you would probably bring in a batch of about 100 packets at any one time, and you would probably spend about 10 microseconds processing those packets back out onto the network, which gives you an average That's based on an application that's doing 10 million packets per second with an average processing budget of 100 microseconds, nanoseconds per packet. And that's kind of the universe that we live in. So if you want to add a cool new functionality to Snabb Switch, you want to add a new device driver, you want to add a packet filtering function, you want to add anything like that, you will write a little Lua object like this that just has a little bit of code that grabs the packets off the link, operates on them the way that you want, puts them out onto some other links. And because we're using LuaJIT, it's incredibly easy to call out to C or assembler or basically any language that looks like C as well. And you don't really have to do everything from scratch. So we have been hacking away and building a small kind of catalog. It's like an app store, you might say, which are just some pre-made processing elements that you can include in an application design and wire together to get stuff done. So these are the ones that we have in our main repository. So it excludes the more application-specific ones that other people have written for their own programs. But I wanted to highlight a few of these. So one of the apps is the Intel 10G. So this is a Lua object that implements the pull and push methods, and it implements a device driver for an Intel 10 gigabit network card. So when it starts, it maps the registers for the network card, it allocates some memory that's suitable for DMA with stable physical addresses and that kind of thing, and it just sets up DMA and just talks to the network card, reads and writes packets. We also have the vhost user app, which is one that we're actually really proud of. The vhost user basically does the same thing, but instead of talking to a physical network card, it talks to a QEMU virtual machine, can very, very, very efficiently get packets in and out of a QEMU VM, and it makes use of a QEMU feature called vhost user that we actually developed, because when we came around to having this requirement, nobody was doing fast I/O on QEMU, so we had to invent it. And that went really well. It was really nicely accepted by the QEMU community and was a great experience. And another last one to mention here is the PCAP filter. This is a cool app. It takes packets in, it applies a filter, and then if they pass the filter, it lets them out again. And the filter is the same language and syntax that you use with TCP dump. So some clever people have written a compiler that takes that syntax, translates it into Lua code that is then just in time compiled to machine code, and it works really, really well. So there's a bunch of apps, and it's growing all of the time, and it's your starting point. So now, having kind of explained the high-level architecture and also kind of what apps we have, I just wanted to show a couple of examples of how you actually solve a problem, how you actually build an application using Snabb Switch apps. So this is how our Packet Blaster application works, which I described as the infinite load generator. So the Packet Blaster is a command line program. You tell it which file you want to blast onto some network ports, and you tell it which ports you want to use by their PCI addresses, and it goes out and in Lua makes a little network like this. So you have a file app that reads packets out of this PCAP file that you've created with TCP dump or something like that, and it transfers those packets out to the T app, which then duplicates them. So it's like the Unix T command. You have one stream of packets coming in, and in this case you have 3 streams of packets with the same content coming out, and then they go into these 10 gig interfaces where they go out onto a network. And just looking at the diagram, you would kind of think that it just sends all of the packets once and then it's finished, but we have a little quirk in our, an extension in our 10 gig driver there, where once the last packet has been sent, we can just ask the NIC to repeat and resend. And this is a really, really efficient way to transmit packets out onto the network. And what it means in practice is that we can, even with the slowest CPU you can possibly find, we can fully load absolutely any number of network interfaces, even if you're using kind of 64-byte packets. It's a really, really practical application because you can generate, for example, 100 gigabits per second of load using just one CPU core, which means in practice you can actually generate load on the same machine that you're testing on, which can make logistics with lab equipment a lot easier. We use it a lot for that purpose. And then, more ambitiously, this is the NFV application. So this is an app network that is connecting 3 virtual machines to a physical network, and it's one of the most complicated applications that we've made yet. So I hope I can successfully explain it from this diagram. Let's see. So along the top row, you have 3 vhost user apps. Each one of these is connecting to a virtual machine. So there's 3 virtual machines doing I/O at the top of the diagram. Down at the bottom, you have 3 10 gigabit virtual functions. So this is using another mode of the Intel 10 gigabit driver where we actually run 3 drivers, but they're all attached to the same physical NIC. And the NIC has a built-in switch that is able to look at the destination address on the incoming packets and choose a different hardware queue based on where they're going. So we can program that switch from our driver so that it knows what MAC address and VLAN each of the virtual machines lives on, and it can automatically dispatch packets in the right way. So from the point of view, it looks like 3 different network cards here. So with the network card on the left, or with the little app network fragment on the left, we have just the vhost user at the top and the 10 gigabit Ethernet at the bottom. And in this case, every packet the VM sends goes straight onto the network. Every packet received on the network goes straight into the VM. This is just if you want to have a clean connection. If you look at the one in the middle, though, we introduce a filter, and it's only hooked in one direction. So you would construct this if you want packets received from the network to always go directly into the virtual machine, but any packet from the virtual machine should be forced to pass through a filter before it's allowed onto the network. So it's a way of restricting egress traffic from a virtual machine. And slightly more complicated is the last diagram over on the right, where we've done some tunneling. So the virtual machine thinks that it's on a network, but it's really on a network somewhere else. So every packet that it sends is encapsulated in an IPv6 tunnel header and sent to a faraway destination, and return traffic is treated in the same way. And this is done, actually, this is implemented with a couple of apps, with the L2TP app that is performing adding and removing the tunnel headers as needed, and then with a small lightweight IPv6 endpoint that is performing neighbor discovery, finding a router that we can talk to, resolving a MAC address and that kind of thing. So this app network here is generated by the Snabb NFV program based on a configuration file. The configuration file says which virtual machine ports you want to connect to, which network resources you have, what all of the MAC addresses are, and how you want to apply various rules. And the initial use case for this is actually for telecom private clouds. So we have an OpenStack integration where we can automatically stay synchronized with the OpenStack Neutron network database, and every time you define a network and define filter rules and this kind of thing, we can automatically sync that in here so that all of the policies are enforced on the hypervisor. And we can do this with drastically more performance than the Linux kernel. So you can use this in practice to do 100 gigabits a second of real ISP traffic on an OpenStack compute node, which is just kind of way more than what you would get out of the box. And that's our project. That's what I wanted to tell you about. You're welcome to come and find us on GitHub, join our mailing list, or anything like that. Thank you very much for your time. Any questions?
In the packet structure, your packet size is 10,240. Is it Ethernet frame size? What's the size? Where the size is coming from?
So the question is our hard-coded packet size enough? If I understand correctly.
Yeah.
Yeah. So far, yes. So if you're designing an application, you're going to decide what are the maximum packet size that you're planning to support. So if you would want to support more than 10 kilobyte packets, then you would need to tweak that number and maybe send in a pull request. But for most applications, about 9500 is where people want to set their max MTU.
Okay, got it. And you also mentioned that you could do some load testing with this. And how exactly would you do it? So would I be able to record traffic and play it back in some way with Snabb Switch, or this is not what the thing is designed for?
So for our load testing, our Packet Blaster application, yeah, it works. So the question was, how do you do load testing with Snabb Switch? And the Packet Blaster kind of front end on Snabb Switch is so Snabb Switch is structured a bit like BusyBox. It's like a bunch of different programs built into one binary. One of these programs is the Packet Blaster, and when you run that, you give it a file name of a PCAP file you want to blast, just blindly replay in a loop onto a network. So you can populate this file with whatever you want. You might have just one 64-byte packet or 500-byte packet in the file that you want to loop, or you might have something more complex. But it's still going to be just blind load testing. So it's very good if you want to test something simple like a switch or a router. If you want something with some TCP logic or something, then it's not the right tool.
First of all, thank you. It looks pretty impressive. Can I use Snabb Switch to build SDN switch like OpenSwitch compatible? Is there any support for that kind of application?
The question is, can you use Snabb Switch to build an OpenV switch compatible? Yeah. So if you want to do the work, yes. So what would that? So OpenV switch is another software switch that is based on this OpenFlow model, where instead of apps running general purpose code, you have flow tables where you would say if the packet matches this flow. So you could implement all of those things in Snabb Switch, and it would be pretty interesting. And actually, when I was starting the project, it was one of the first application areas I was thinking about was whether we should use it as an OpenFlow data plane. But I think when I talked to people in the OpenFlow world at that time, what they told me was that the problem that they're working on in OpenFlow is that they need to have applications on the controller side, and it's only once they have that they really have a problem worth solving on the data plane side. So you could do it, but from what I can see, the OpenFlow world is pretty well served by OpenV Switch already. So I don't know what we would contribute to that today. Maybe it will be another story in the future.
Okay, thanks.
Okay.
Thank you very much.